I want to discuss about this answer for quiz. Okay, let's see. The question is, write the expression for region R. Okay, so we need to define this region. X goes from A to B, and then Y should go from C to D. Okay, in this case, this is not a rectangle. So since this is not a rectangle, you cannot have a constant value on the boundaries on the left and also the constant values for boundaries on the right. So because this is no longer a constant. Okay, in that case, you need to define the boundaries for each sides. Okay, let's see this one. Let's try to start with these points. So these points, and then run along y direction. Okay, so at this point, y goes from 0 until, and then exit at y equals to, let's look before that, sorry. So this one is what? This one is the equation when the slope is 3x and then the y intercept is 6. So this is y equals to 3x plus 6. And then the equation on this side is, this is a negative slope, so minus 3x plus 6. So this is y equals to 1. And then the bottom boundaries is just an equation of y equals to 0. Okay, so in this case, let's pick one point, and then run along y-axis. So this is like a y constant. And then it seems like, sorry, x is constant. It seems like if you pick at this point, and then you will exit at this point on y equals to 3x plus 6. Okay, but if you go on the right hand side, if you go pick one point and then you run along y-axis, you will exit on this line. Let's say this is y1, this is y2. You will exit on y2. So this is not the same. So even though your starting point is the same, but your exit point is not the same. Okay, therefore you cannot do like this. So macam mana nak buat? So I need to reverse my starting point. Okay, let's say if I start from this point and then I run through x-axis, I will exit on y2 lane. So this is y1 and then y2 line. Okay, and then if I go from this, I also exit from the same equation. So in that case, I can say like something like this. So in x direction, this is in x direction. Siapa yang kena tangkap polis tu? Okay, so maksudnya apa? Maksudnya in this case, kalau dalam in x direction, saya masuk daripada kiri, saya keluar daripada kanan. So saya bertembung dekat line y1, saya keluar daripada y2. Okay, in this case, in that x direction, so saya kena tukar saya punya equation. So tadi yang y1 equals to 3x plus 6. So saya nak kena tukar. So just put for x1. So that will be x equals to y minus 6, y1 minus 6 over 3. Also this one is minus 2. So this is for x1. So x1 is coming from the left hand side, from the left, and then y2 correspond to the exit point in x direction. So x2 is just the flip of that one. So this is just 2 minus 2 minus y2 over 3. Okay, so in that so if you go along starting from y equals to 0, you also meet at x1 and then exit at x2. If you go along topmost, you also entered at x1, left x2, and then so on. So in this case, y should goes from 0 to 6. So because it goes along this line, 0 to 6, but now x should goes from x1 and then x2. Okay, so the proper expression for r should be r just equals to the set of point in xy such that y goes from 0 to 6 and then x goes from y1 over 3 minus 2 and then y2, sorry, 2 minus y2 over 3. So that's how you do your expression for r. You cannot have, if you put something like x goes from -2 to 2, it means that this is a box, a rectangular box, which is not true. Okay, so that's how you write the expression for r. Find the region first. And then how to find the appropriate expression to find the volume. So this is to double integration. Okay, so since we don't have, since we have x as variables, so in that case, we need to put, this is goes from x1 equals to y1 minus y1 over 3 minus 2, and then from until x2 equals to y2 minus x2 over 3, and then anything fxy. I don't know what fxy is, just write fxy. And then x is now not a constant, so we put dx and dy outside as constant. So that's how the problem goes. Okay, so any question on that? Okay, no question. Okay, so let's go for change of variable. So last time we did change of variables from uv to xy. Okay, let me reiterate what we did last time. So if we have parametric equation, so let's say x is defined by some function u and v, and then y is some function in terms of y, u and v. So this is called parametric equation. This is called. Because you define into some variables. All right, so this means that x and y, sorry, another one. So for plane of u and v, so the coordinate in xy is just a transformation from u and v. So in that case, if you have like rectangles, let's say this one is in u and v, and then you can also have something like the transformation is somewhat like a parallelogram. Okay, so this is a transformation from this to that. It may not be linear. This is linear. It may be something like points. Okay, as you can see that what we did for last time, when you have a rectangle and then like this. This is from last class. Okay, saya perasan ada orang buka mic. Boleh saya boleh dengar.
Doktor boleh mute kan kot?
Ya, saya boleh ni. Okay, so in most cases, kemungkinan rectangular become parallelogram. So this is parallelogram. and then it might not be linear in this case. Let's say this is from R to S, and also from another S, something like this. Okay, so for change of variables, if you remember from last time, we did something like this, integration. So this is double integration. So from region R for fxy dA, this is equals to the transformation on region S in terms of f, x in terms of u and v, y in terms of u and v, and then we have something called Jacobian, the Jacobian of u, x, and y, and u and
Sorry,
v.
Doktor.
Yes,
Doktor.
yes.
Kita orang masih, slide kita orang masih dekat quiz 3.
Masih dekat quiz eh? Oh, okay. Nampak ke?
Nampak dah. Terima
Oh,
kasih.
dari tadi lagi tak nampak eh. So saya lupa nak ni. Okay, so yang tadi saya nak repeat what I said just now. So we have parametric equation, x in terms of u and v, y in terms of u and v, and x and y is just a transformation from space u and v. Okay, you can also, this is, and t is 1-to-1, 1-to-1 transformation. You can also understand in one that this is 2-dimension, so 2-dimension, yes, 2-dimension. In 1 dimension, transformation is just, this is in 2D, 2-dimension. And then in 1D case, the transformation is the same thing as f, because you can also have f inverse. So it's the same same analogy in 2D. Okay, so the double integration, if you want to do some change of variables in terms of general variables u and v, in this case, last time we did for polar coordinate. So in this case, we need to multiply by Jacobian, and this is dA in terms of u and v. You're not sure yet, is it dv or du or dv? The order is not, it's not yet defined. Okay, so what is this part? This is called Jacobian. And notice that this is absolute values. Why? Because this Jacobian might give you a negative values, and for area to be negative, it means that it's on the other side. So intuitively, area should not be negative, but it may be on another position. Okay. Okay, let's see. How does it the Jacobian comes from? Okay. Let's see. Awak pernah dengar ke Jacobian ni? Mungkin awak pernah dengar dalam linear algebra?
Chapter 3.
Chapter 3 eh? Chapter 3 kita punya ni ke? Subject? Alright. Kita tak ada masalah lah kalau macam tu. Okay, so maksudnya apa? Definition untuk Jacobian. Kita tulis nanti. Okay. So how do you define this? Okay, kalau let's say I have this this space, let's say in space u and v, Okay. And then point di sini adalah U0 and V0. Dan point di sini adalah so change in U. So this is change in U. So this is just U0 plus delta U and then V0. So V0 tak berubah because this is on y-axis. So this is U and V space. And then these points correspond to change in delta V. So this means that this is delta V. Okay, so it means U0 and then UV plus delta V. And then therefore this point is the whole thing. Okay. And then after some transformation, doing some transformation, it will become something like this. Okay, so this is on XY direction, XY space. Okay, so meaning that it's no longer a rectangle. Okay, so macam mana saya nak approach benda ni? Saya nak approach dia punya apa ni? Scaling factor. So this, let's say this is R goes to S. Okay, and then in this case we have dA of UV, and then in this case we have dA of XY. Okay, so dA of UV equals to, is it equals to dA of XY? Jadi, tiba-tiba jadi close pula. Okay. So is it going to be the same? Not necessarily the same. Okay, kalau dia part 2 by 1, it might be. If not, then is it equals to dA of XY? Okay, sebab saya nak cari dia punya vektor. Okay, so ada dua cara untuk faham benda ni. Saya tunjukkan cara yang pertama dan nanti saya akan tunjukkan cara yang paling mudah awak nak faham. Okay, cara yang pertama, I just took this as, let's say this one is, let's take the vector right here. Let's say this is vector R. Let's say this is R of this in terms of U, because this is in U direction. So this is correspond to this R. So R can be anything. R boleh juga, R can be, this is R of U. R can also be in this direction. This is R sub V. So derivative in terms of V. Okay, so vector kat sini is R of U. And then the length is change in delta U. Okay, and then kalau saya ambil this another vector in this direction, this is R sub V, and the length of this is delta V. Okay, so kalau saya nak cari the dA, the small area in this particular parallelogram, so this is dA. So the dA of this partially should be This is approximation, not yet the whole thing. So the delta A in this small area is just the magnitude of RV. We use this notation, RU first, RU, and then delta U cross R of B, delta B. Okay, so this is just the approximation, so still in delta. Okay, so I can take out, so I take out U and V, sebab apa? Because this one is constant, so it will be left with R of U cross with R of V, and then delta U, delta V. Okay, so kalau saya ambil really tiny, take the limit as n goes to infinity. Okay, kalau saya take the limits delta A, I can say something like this. So limit Sn delta V and delta U goes to infinity. So this is the limit. So the concept of limit is just, so dA is just R of U cross of R of V times du dv. Okay, so just take it. Okay, let's try to evaluate this part, R of U and then R of V. So if you remember, I did right here above, the parametric curve is in terms of U and V. So in this case, if I want to represent R, this is R equals to X UV of I plus Y UV of J. Okay, so in that case, if I do some partial derivatives of that and then cross the product, dia akan jadi, so this means that partial of R, partial of U, cross partial of R, partial of V. So this is just equals to, if you remember the cross product, it's just I, J, and K. Okay, so I correspond to partial of X in terms of U, and then J correspond to partial of Y in terms of U, and then partial of X in terms of V, and then partial of Y in terms of V. How about K? K is 0 because we don't have any vector in terms of K. Okay, ada persoalan setakat ni?
Tak ada.
Tak ada. So yang ni direct daripada awak punya ni. So in this case, kalau awak tengok, if you look at this part, this is 0. So meaning that if I have PKP pun ada ni. So maksudnya apa? Maksudnya kalau saya buat apa ni, this derivatives, so not derivative, this determinant, it will be for X determinant, it will be XU, for I determinant will be this times this, so it will be 0, and then also this times that, it will be 0. So the only thing that is left is just K factorial, K factor. So it will be just X U and then X of V, Y of U, and then Y of V. And then so this is just K. Okay, so kalau K ni apa? So K is just a unit number because this is in terms of vector, so it's just a unit number. Saya ada buat ni ke kat situ? Ada error ke kat situ? Saya rasa tak ada. Okay. So the Jacobian of this is just Jacobian of the whole thing is just of U and V is just the determinant of this matrix, which is X U times Y V minus X of V times YU in absolute values. Okay, you can also change in terms of this. So this is equals to, you can also change into this part, X of U and then X of V and then Y of U and then Y of V. So I think that's better visualization. So the whole thing will be just anything. So the row is in X and then the column is in Y with respect to the first and second derivatives of U and V. Okay, so that's how, so this is just like a scale. Dia macam scale daripada ni. So in this case, delta X, delta Y. So we can put into this equation. So dA of XY space is just equals to the Jacobian of U and V in absolute values times dA of UV. Okay, let's see some example. Let's see what we did in polar coordinate. So in polar coordinate, we say that the region R in fxy dA is equals to region in S f of R cosine theta, R sine theta, and then this is R dr d theta. So in this case, this is example in previous double integration. So in this case, we can see that the factor is now, it has, in this case, we can see the Jacobian of R and theta is just R because this is the scaling factor and this is just dA in terms of R and theta. Okay, let's see how does it goes. Okay, we can see that X is R, let's see, X in terms of R and theta is just R cosine theta, and then Y in terms of R and theta is R sine theta. Okay, so the Jacobian of R and theta is the matrix of delta X in terms of the R, and then delta X in terms of the theta, partial X. Okay, and then the second row is partial Y in terms of R, and then partial Y in terms of theta. So the determinant of that is just what? X in terms of R is just cosine theta. And then R cosine theta in terms of partial derivative is just minus R sine theta. Okay, so this is partial derivatives. X in terms of R, and then this is X in terms of theta. Okay, let's see how about the y variables. So this will be sine theta, and then it's just r cosine theta. So in this case, this is for y partial r, and then this is y partial theta. Okay, let's solve this. So this is equals to r cosine. So this is multiplied by that one. So r cosine squared theta minus r sine squared theta. Because multiply that one. Okay, so now it becomes r cosine squared theta plus r sine squared theta. So this is just r times 1. So this is just equals to r. So we can see that this is the same thing as what we anticipate before. So the Jacobian in polar coordinate is just r. Okay, now let's see what happened for Jacobian in triple coordinate. Let's see example. Not triple coordinate. Maybe I can say something like in spherical coordinate. Okay, what does it mean spherical coordinate? Awak pernah belajar ke spherical coordinate sebelum ni?
Tak.
Tak pernah. Masa apa ni? Masa apa nak tanya ni? Masa perkenalkan multivariable tu tak ada eh? Tak ada. Okey, so tak apa. Okey, sebelum saya pergi ke ni, apa beza di antara spherical coordinate dengan polar coordinate? Okay, spherical coordinate, let's see, the difference between spherical and polar coordinate. It's actually almost the same, but it has a little tiny difference. Okay, let's see this one. This is in 3D. And then let's see in 2D. Okay, so in, let's say I have a circle, and then in this case I have a sphere. Okay, that's how. Okay, in polar coordinate, so this is, let's say this is polar coordinate. So we have this, it's not at the center. So this is theta, and then this is r. Okay, so it was something like you can also have several rectangle, not rectangle, circle, not into shape, something like that. The theta goes from 0 to 2 pi. It's always like that, 0 to 2 pi. And for any circle, it always goes from 0 to 2 pi. But the only change is the r. So let's say this is r1, and this is r2, and this is r3. So the only changes is the r. Okay. And then in spherical coordinate, it's mostly complicated because now we have z in terms of what? In terms of radius theta right here, and then you also have an angle right there. This is phi. So z is no longer like a constant, but it's also in terms of angle. So that's the only difference. In this case, in polar coordinate, you don't have to worry about angle in z direction. Okay, so what's the parametric equation in spherical coordinate? Okay, so we have x is in terms of in terms of rho, and then it might not be in rho and theta, and then phi, and then we have y also in terms of rho, theta, and phi, and then we also have z in terms of rho, theta, and phi. Okay, what does it mean? So r in this case, the rho right here is for radius. Theta is the angle between x and y. And then phi is the angle between z, x, y. So maksudnya kalau saya tengok kat sini, this is true direction. Okay, so this is theta. And then this is, let's say if we have another one. So this is z, susah nak nampak kat sini. So this is the angle phi. Okay, so kalau ataupun kalau awak nak tengok dalam case bola, tengoklah bola kan dia ada benda ni kan, dia ada macam ada line kat situ dan dia ada line kat sini. So angle in this line, so the angle in this line is theta, and then the angle on this line is phi. Okay, and the radius is rho. Okay, so in this case, what's the parametric equation? It was given by x equals to rho sine of phi cosine of theta, and then y equals to rho sine of phi sine of theta, and then z is just rho cosine of phi. So this is the parametric equation. I think it's quite simple to memorize this. Okay, now we want to find the equation for triple integral. So before that, we need to find the Jacobian of that. So the Jacobian of phi, theta, and rho, phi, and rho, theta, and phi is x in terms of r, and then x in terms of theta. So this is rho, x in terms of phi, and then y in terms of phi, rho, and then z in terms of phi. Okay, I don't want to evaluate this because I think you already learned how to evaluate 3x3 determinant matrix. So if you do the math, the output will be rho squared sine of phi. Okay, so just take my word for it. You try on your own. So solve this, and then you get this equation. Okay, so how do I put it into triple integral? So this is the region R. Region R for f, x, y, and z, and then this is dv. So now it becomes a volume. Sorry, I think we need to change this. Let's use generic for g. So this is limit, let's say in g, whatever that is. I want to use maybe use I, big I, and then it will be f in terms of rho sine phi cosine, what's that, cosine theta, and then rho sine phi sine theta, and then rho cosine phi. Okay, and then this will be rho squared sine phi, and the order should be d phi, d rho, d phi, and then d theta. Okay, usually in this order. In this order. Okay. Any question? So this is just change of variable as long as you know the transformation equation. Okay, so this is the thing is how to get this. In most cases, in most particular cases, this is not already defined. So this is easy because why? Because it's already defined in spherical coordinate, but it might not be this easy. You need to find on your own. The same thing, similarly, you want to find u substitution, for example, if you have e to the x squared. So you need to find on your own x squared equals to v, something like that, not v, u. Okay, you need to find on your own. So in most cases, it's not that straightforward. Okay, let's see. Let's see some example. Evaluate example. Evaluate region R for exponential of x, y, dA. Okay, and then region R is enclosed by lines y equals to 1/2 x, 1/2 x, y equals to x, and hyperbolas. Y equals to 1/x and y equals to 2/x. Okay. Let's see this region and look at this one. This is the fxy. Okay. So as you can see that this region, we need to find how does the region look like. Okay, so let's try to before, if we have something like this, it's not given, then you need to look at the picture of it. So if you plot this, how does it going to look like? Okay. So let's see, y equals to 1/2 x. So y equals to 1/2 x. So this is like 1/2 of the slope. Let's use a straight line. So this is 1/2 of the slope, something like that. And then y equals to x. So this is another line, y equals to x. Okay, so this is y equals to 1/2 of x, y equals to x. And then hyperbolas of 1/x. So 1/x is something like this, not to scale. And then 2/x. So this is another one, 2/x, like that. So the region is this region, the enclosed region. Okay, now how can I do this in terms of in terms of x and y. You can see that this is quite difficult to approach if you do the direct iteration on x and y. Why? Because let's see, if I pick one point on x direction and run through y direction, now yes, I have unsteady hands. So if I pick this line and then I go through y direction, you can see that I go from this line and then exit on that line. But if I have another one, another point, if I have another point right here to there, I enter on a different line and also exit on another different line. Okay, so you cannot do directly like that. So in this case, I can choose to use change of variables. Okay, so how to do that? Let's use how to choose the change of variables. Okay, from this equation, I can see that from this equation, and this equation, I can do some manipulation so that the right-hand side is a constant. Okay, I can do the right-hand side as a constant, so I can say y equals to x over 2, and therefore, in this case, I can say y over x equals to 1/2. So my right-hand side is now a constant. And then y equals to x, and therefore y over x becomes 1. So I have a constant on right-hand side. Okay, and then on this hyperbolas, I have y equals to 1 over x. Therefore, x times y equals to 1. And then if I have another one, what's that? 2 over x, y equals to 2 over x. Therefore, my side will be xy equals to 2. Okay, now I have, this is in terms of y and x on the right-hand side, and then on a left-hand side, on right-hand side is just a constant. Okay, so what to do? So I can say that, let's say this one equals to u. This is, let's try to say that again. Okay, I can see that I have this y over x, and then I have xy, and this is just also xy. So I have like two similar equation. So I can say, let's say, let now u equals to y over x, and then v equals to xy. So this is a similar analogy that you do in one-dimensional case, one integration, single integration, same thing. This one involves two variables. The other one before in math, calculus 1, you do for one variable. So it's just add another variables. Okay, so what does it mean? It means that now you have like u equals to 1/2, and another equation you have u equals to 1, and then you have v equals to 1, and also v equals to 2. Now if I put it into the new transform coordinate, okay, so I put it into new transform coordinate, I will have u equals to 1/2, let's say maybe this line, okay, and then u equals to 1, so this line, okay, so this is u equals to 1/2, u equals to 1, because this is u axis and then this is v axis, and then v equals to 1, so this is at the bottom part, and then last one v equals to 2. So this is v equals to 1, v equals to 2. Now we have an easy region, let's say this is region S, to integrate. Okay. Why? Because you can see that the limit on the lower boundary and the upper boundary is just a constant. You can see that u goes from 1/2 to 1, and then v goes from 1 to 2. So this point, anything inside this region. Okay, any questions so far? Okay, so we knew this transformation. Now we need to find the Jacobian. Okay, so the Jacobian is in terms of u and v. So in terms of parametric equation, u and v. So you can see that after some manipulation, you can see that x in terms of u and v. Next step, maybe I should goes on the other side. Find Jacobian. So you need to find the equation x in terms of u and v, and then y in terms of u and v. Okay, so after some manipulation, you can see that x is just square root of u over v. And then y is just square root of u times v. You can try do it on your own. Try to look, does it make sense? Okay. Okay, so now what's the Jacobian of that? So partial of x, y, and then partial of u and v is just x in terms of u, x in terms of v, and y in terms of u, y in terms of v. All right, so that will be minus 1/2 of square root of v over u, because that will be minus 1 squared. So I just flip the variables, and then in terms of u it's just 1/2, in terms of v it's just 1/2 of uv. You can try to do it on your own next time if you want to. So this is, and in terms of y uv, so that's just 1/2 of v times u, and then 1/2 of u over v. So do the math, and then your answer will be minus 1 of 2u. So you can do the math. Okay, now let's plug into your the double integral. So this is r exy dA. Okay, now we can put the limit. So in this case, it doesn't matter if you want to put in terms of u, v, or v and u, y, because the limit is just a constant. Okay, so let's try to use du dv. it doesn't matter, but just like x, y, just use x, y, z, something like that. So v goes from 1 to 2, I suppose. Yes, v goes from 1 to 2, the outer integral. And then the inner integral goes from 1/2 to 2. And then your exponential is exponential of x and y, so that's just v. And then the Jacobian of that is minus 1/2 to u. So why? Because you remember, so dA in terms of xy is just the Jacobian absolute values of dA in terms of uv. So this is just equal to, from this one, it will be the absolute of 2u du dv. Okay, do I need to evaluate this? I think this is easy for you. You can use the iteration integral, because now e of v is a constant. You can take it outside of the variables. And then 1/2 is also a constant, so you can take it out of variables. This is positive because this is absolute values. And then this is just 1, 2, the exponential of 1/2 of 2, and then 1 over u absolute values du dv. So you get natural log, and then evaluate from 1/2 to 2, and then exponential. It's quite easy. So the answer will be 1/2 of exponential of 2 minus exponential log of 2. So this is the answer. So the thing is, the important thing is, I know that you can do the integration, but the problem will be how to set up the integration in 2D. Okay, let's take a break, and after this, we'll get to how to integrate triple integral. Okay, let's go for triple variable, triple integral. Okay, so in triple integration, we have integrate. Use the same if you want to use the same discretization. So you divide x, y, and z into so you divide x, y, and z into a small box. I already gave you the formula for triple integration, but this is just the same thing. Let's say use triple integration. Same thing, it can be in x, y, z Cartesian coordinate. It can also be in polar coordinate, and it also can be in spherical coordinate. Okay, what nice about polar and spherical coordinate is that you don't have to worry about whether is it going to be dr d theta or d theta dr, because it always dr d theta. So you don't have to worry about the order of dv. So, but in general case, that is you need to worry about. Okay, so the definition for triple integration is you have the limit, say in general area of G, in G, I have f, x, y, and z dv. So it's just like you are taking the limit as n goes to infinity for k equals to 1 to n, and then you have f x star k y star of k, and then z k of star, and then you have a little volume v k. Okay, so you have, for example, if I have this in 3D, so this is the small volume that I'm looking at. So this is the dv. Just, and then if you have a really big solid, you can just take the summation of it. Okay, so that's the definition. And then how does it looks like in dx, dy, and dz? Okay, so in general case, if you have a region of G, f, x, y, and z dv, you can have as many as five different combination. Let's define G is the region between, let's say G is region for x, y, and z, when x is between A and B, y is between C and D, and then z is between R and S. Okay, so this is like a box, so like a cube box, something like this. Okay. Okay, so this is from A to B. This is in x-axis, and then C to D in y-axis, and then you have R to S in z-axis. So this is like a box. Okay, so you can have as many as 5 combination. One, I can just do some like 3 of that. I can do something like this. Integrate in terms of AB, CD, and then RS, and then I have F. I don't want to write the whole thing, so it will be dx, dy, and then dz. So you can also use the iterated integral. So you keep one variable, and then the other variable are constants. So just do the same thing. Okay, you can do this. And you can also have, I don't want to write the whole thing, but you can understand it already. So this is the boundaries. I don't know what that is. So fx, y, and z. I can also have dy, dx, dz, and so on. Okay, so you can have 5 many different combination. Okay, then you can do that. And the same thing if you have change of variable, you need to use the Jacobian of that. So if you have triple integral in region G, fx, y, and z, and dv, and then I want to go to region I is the region. Let's say I have x y, and z. And this is a transformation from u, v, and w. Okay, so this is du, dv, dw. Here I can have, this is the same thing, x, f in terms of u, v, w, and then y also in terms of u, v, w, and then z in terms of u, v, w. And then I have the v that, okay, I can have the Jacobian of that. I have dv. Okay, so what's the Jacobian of uvw? So the Jacobian of uvw is just the partial for x, y, and z with respect to the partial of u, v, and w. So in this case, this is just partial x, partial u, partial x, partial v, partial x, partial w. And then the second row will be y and u, y and v, y and w. Lastly, the last row, the z of u, z of, let's write it properly, z of u, partial z of v. You can see the pattern, partial z of w. Okay, so for example, if I might not have x, y, z, but I have, you can apply to a higher dimension. For example, if I want to have x1, x2, x until x of n. And then this is correspond to the space of, let's say, x, y. Again, maybe this is u1, u2 until un. So this is the same algorithm. Okay, let's see one example. Okay, and before that, I forgot. Same thing in double integration. You have type 1 in double integration. You have type 1. Okay, so type 1 is when you the y is a variable, and then you also have type 2. Okay, therefore, because you have double integration, in triple integration, so if it's triple integration, it means that you have to add one more type, type 3. Okay, so what does it mean by all these 3 types? Okay, let's try to visualize this. You have a plane, x and y. Okay, if the projection, say projection, let's talk about the projection. If the projection, yes, let's say I have some potato up here, a solid potato up there. Okay, so if the projection is onto xy plane, so this is type 1 because this is x and then this is y plane. So this is projection in type 1. And then if I have projection on y-z axis, let's say on this, not y-z, y-z space, y-z plane, say on this plane. Okay, so this is on, let's use this color. this color. So this is on YZ plane. This is type 2 triple integration. So this is type 1. Let's use it on. And then if I project this onto YZ or XZ plane, so let's say this projection. Okay. So this is type 3. You don't have to remember, but you need to know what's the key point in this particular problem. Okay, what's the key point? Let's take an example of a solid pipe. Okay, imagine I have a solid pipe. A solid pipe like this. Vertical, and I planted this vertically. Okay, so in this case, I think that if you're looking on this direction, so if you look at above that point of view, you can see that this is on, let's say, XY plane. So if you put it into this plan view, this is just a circle. Which is easy to integrate. And the length is just, let's say this is a number, let's say this is just K, Z equals to K. So Z goes from 0 to K. So that's why it's easy. Okay, now let's change the position of this pipe into this position. Okay. Now, if I want to find the volume of this solid pipe, okay, and then if I look on this direction, I can see that the projection is on XZ plane. Let's use a similar color. So the projection is on the XZ plane. Same thing that if I want to orientate my pipe on the other direction, say this direction. So this is on YZ plane. Okay. So because why? Because let's see that this now you need, this is correspond to your dV. Okay, in this case, let's say in this case, this is just integrate, double integration. Might use a better color. Let's use yellow. So if I want to integrate this one, integrate this triple integral. So I will only evaluate, firstly, I need to evaluate the dA. So I can say like this. So Z is just from 0 to K. Okay, and then I have function of X, Y, and Z. And then I have dA of dZ. I forgot to write that one. So in region of R. Okay, so you can, this is easy to evaluate. Same thing for this one. For this one, so the only thing that change is, the only thing that constant is Y. So I can rewrite my triple integral as from y from, let's say, y from c to d. I want to use 0 because it might be not non-zero. And then I want to integrate the region of f x, y, z onto dA on space x and z. And then I forgot to write this one, a in terms of x and y. This is dy. Okay, and then how about this one? This one is also the same thing. So the only thing is good about this is now x goes from a to b. So I can evaluate from a to b for region R on xy xz plane. Let's see, did I now this is yz plane. Okay, I made a mistake over there, but the notation is correct. XYZ, and then I can evaluate dA in terms of y and z plane, and then this will be times dx. So the only thing that's different, you need to be careful about is this order. This order. Okay, so this doesn't involve any Jacobian because we don't have any transformation. Unless you want to do the transformation, then you need to pay attention to the Jacobian coefficient. Okay, let's see an example. Evaluate say from 3 minus 3 to 3, from minus 9 minus x squared, and then positive 9 plus x squared, and then from 0 to 9 minus x squared minus y squared. This is the function of x, y, z is just x squared, and then dz, dy, dx. All right, so from this, you can see that you can see that this involves like a circle, x squared and then y squared. So this involves a circle. In this case, you don't have to worry about the order. Why? Because it's already stated in the question. So, but if you want to look at the deeper part of that, you can see that this is like a circle. Let's try to break out the circle. Okay, so the inner part z goes from 0 to 9 minus x squared minus y squared. So I can break out. I can say this is just z equals to 9 minus x squared minus y squared. So it goes from 0. So it's above the xy plane. And then when z equals to 0, say when z equals to 0, so this is just a circle, x squared plus y squared equals to 9. Okay. So in this case, if you plot if you plot the figure, you can use the website that I gave it to you. If you plot this, it will look like something like this, like a circle on XY plane, and then this is like a parabola. Okay, something like that. Okay, so this is the equation for x squared plus y squared equals to 9. Y is 6 equals to 9. And then this is the z equals to 9 minus x squared minus y squared. So this is like an inverted bowl. Okay, so in this case, this is type 1. So what you do is find the area first, and then you can evaluate the integral. All right. So what's the easiest part to do about this? So I think that why don't we use cylindrical coordinate? Okay, so this is cylindrical coordinate. So this is correspond to the polar coordinate. Okay, so how can I change the variable? So I can say r equals to, x equals to r cosine theta, and then y equals to r sine of theta, and then x, y, and then z equals to just a constant. What constant? Maybe I can say k, because it's not related. It's just one. You can see that this is x squared. So I can also, if I want to put this, I can say something like this. So x is just, so in this case, I can put z equals to x squared minus y squared. So this is like k minus x squared minus y squared. So this is just k minus r squared cosine squared plus r squared sine squared. So this is just k minus r squared. So k can be anything. So this is just the equation of this particular point. Okay, so we knew that k is 9 because the height is 9. So in this case, k is 9. And then how about r? R is 3. So in this case, we have z equals to 9 minus r squared, because k is the height of this one. And then x equals to and then y equals to and then how about the Jacobian of that? So the Jacobian of that is just you take partial x, y, and z, and then partial x, theta, and phi. If it has phi, Okay, hold on. Before that, hold on. Because I need to approximate the area first. Okay, I forgot that. I need to approximate the area first. And then after that, I can just times the Jacobian. Okay. So in this case, I actually did this already. Okay, so in this case, if I translate directly into this integral, okay, this is from your calculus one. Okay, so this is from your calculus one. Let's try rewrite that again. -3 to 3. So x goes from -3 to 3. Okay. And then y goes from this -9 minus x squared. And then square root of 9 minus x squared. You need to do the conversion. After this, x minus squared minus y squared, and then this is x squared dc dy dx. Okay, and then this is just equals to the triple integration in area G, which is x squared dv. So I want to do the change of variables after that, and then this is just integrate in region of, let's say, from in dA region from 0 to 9 minus r squared, because this is 0 to x squared minus y squared is r squared. And then I need to change x squared, so that one becomes r squared cosine squared theta. And then the dz is just dz. So the position doesn't change at this time. And then I can also evaluate this as dA, the whole thing. So now I can get rid of z-axis, and then after that I can do the area integration. Okay. Hold on, kejap saya terganggu sikit tadi. Let's see. Hold on 1 second. Okay. You can do the integration. So this is just direct integration. But how about this dA? So dA, so now dA is just the projection on xy plane. Okay, so this is just the projection on xy plane. So now I don't have to calculate the Jacobian, because I know that the factor will be just r dr d theta. You don't have to do one more time. Okay, so I can just write this in terms of dA. So this is just write the whole thing. So this is just into the region of 0 to 9 minus r squared cosine squared theta easy, and then it's just times r dr d theta. Okay, so in this case, I can just r, you can put it inside, so it will become r cube. Okay, so I can just put it inside here. It will be r cube. And then I need to define my region for R. R goes from 0 to 3 because the radius right here is 0. So the radius here is 0. And then the limited by 3. Okay, so this is just from 0 to 3. And then how about the theta? Theta is just the angle starting from this line, this position until that position. So it means that it goes from 0 to 2 pi. So that's just the setup. So in this case, you don't have to worry about the Jacobian because this is cylindrical coordinate. This is just direct, straight to the point. Because we have dA only on the XY plane. Okay, so if you do you want me to? I think yeah, just do one. I always didn't finish my evaluation. So let's try to evaluate this. Okay, now Z is from, you can see that this is just a constant in terms of Z. So in terms of Z, this is constant. So I can just put it like Z exists. So multiply by Z. So this is from 0 to 2 pi. I don't want to write the whole thing. Okay, let's try to do it one separate problem. Okay, so the inner integral from 0 to 9 minus R squared, R cubed cosine squared theta dz. Okay, so Z is so that is just constant. Everything in this case is a constant because it doesn't has any Z function inside. So this is just R cubed cosine squared theta from 0 to 9 minus R squared dz. Okay, so this is just R squared cosine squared of theta multiply Z from 0 to 9 minus R squared. So that one is 0. So we be left with just 9 minus. No. Let me see. Yes. So Z is that. So we'll be left with 9 minus R squared. So 9 minus R squared. Okay. So we need to solve this because the next variable that will be integrate is dr. So we can do this. This is like 9R cubed cosine squared theta minus R to the power of 5 cosine squared theta. All right. So I can factorize cosine squared. I think that's easier to do. So that will be 9R of cube minus R to the power of 5 cosine squared theta. Okay, now it's much TD. Okay, so now the integral the next integral is just from 0 to 3, from 0 to 2 pi of 9R cubed minus R to the power of 5 cosine squared theta, and this is dr d theta. Okay, so the same thing, we take the inner part, Okay, so the inner integral So this is just from 0 to 3. Okay, 9r cubed minus r to the power of 5 cosine squared dr. Okay, so you can see that cosine squared has nothing to do with radius. So you can take it outside. So this is just cosine squared theta from 0 to 3, 9r cubed minus r to the power of 5 dr. Okay, so you can use solve this? Yes, of course. So that one is just cos squared theta of, this is multiplication, 9r to the power of 4 divided by 4 minus r to the power of 6 divided by 6. Let me know that if I go beyond the time. Okay, so from 0 to 3. Okay, so you do the math. That will be, what's that? That will be to the power of 4. So that is 243 to the power of n divided by 4 and times cosine squared theta. Okay, so now you have to be careful with your calculation, arithmetic calculation. Okay, and then the last part is the theta. So theta goes from 0 to 2 pi of 243. I just take it outside because this is just a constant. I want to ruin my equation. Cos squared d theta. Okay, so this is, you can do multiplication, you can do substitution, and so on. Okay, and then the answer will be 243 over 4. Okay, you can do the half apa dia nama dia? Half angle formula, and then the answer will be pi over 4, just pi. Or you can do any techniques. So that's the answer for that. Okay, any questions so far? So you can see that the difficult part for this is which the v in terms of xyz you are going to use. Okay, but once you find it, find the space of projection, then it will be easy for you. So in this case, you cannot change because it's already given. So that's the easy part of this one, because you don't have to change. But if it's given like in terms of general equation, then you have to figure out how to do the problem. And as I told you, the easiest part is polar coordinate and spherical coordinate, because you don't have to change the order. It's always the same thing. Okay, so I think that if you don't have any question, let me see, are we on the right track? Okay, yes, so that's it. Okay, let's see one more example. I think this is a very good example because you can look into several points. Okay, let's see this one example. Last one. I might not be able to finish, but I just want to give you an insight of how you can approach the problem. Let's see this one. And I have a line goes from here to here, and also a line from here to there, and then this line. It's not that straight. Okay, so the region is, you can see that this is the solid part. This is the solid, like you can see this is like a diamond or something like that. Not exactly a diamond, but so it looks like this. Solid. Fill up. Okay, so in this case, you can also look into several ways, several direction. You can look on this view. Okay, you can also look on this direction, and you can also look at, so that's just the direction of that, and then you can also look at this direction. So in all three directions, it looks like you can approximate, not approximate, the shadow will form a triangle. So let's try to look at on XY plane, the plane view. So this is Y, this is X. So if you look at on this direction, let's say this is direction number 1 for type 1, and then this is direction number 2 for type 2, and then this is the direction for type 3. Okay, so if you look at the direction, you are going to see a triangle. Just a triangle like this. And this is the region that it was projected onto. So this is type 1. So you can see that X goes from whatever that value is. Let's say this is B, and then this is C, and then this is S. Okay, so X goes from A to B, and then Y goes from 0 to whatever the equation is. Let's say this is Y equals to, let's say, C minus MX. This is something, just general equation. Okay, so in this case, you can use also, for example, if you go from onto another view, let's say this is XY plane, not XY, YZ plane. This is Z axis, and then this is Y axis. It also form a triangle. Now, the only thing difference is that the equation, the limit is now from this to that. So in this case, it's not a problem what type 1, type 2, or type 3, because all three seems to form a triangle. As long as you know how to use it, then it will be a no problem. Okay, so I think that this is called, by the way, this is called tetrahedron triangle. So this is called tetrahedron. Why tetrahedron? Because you have this axis and that axis. Okay, So that in chemistry, this is like a tetrahedron. Okay, so I think we finished at this point. Any questions so far?